The last day of Youth in High Dimensions, and we'll kick off the day with Freya Behrens from EPFL, and she'll tell us about model systems for attention, structure, and memory in transformers. Freya, take it away.
Thank you very much. Yeah, and thanks also for putting this nice workshop together and the nice evening yesterday as well. It's a beautiful occasion. So my talk is going to be maybe in a slightly different register from what you've seen so far, because what I want to focus on here is looking a bit more at the phenomenology and kind of putting a few of the details of the under the rug, but kind of get the benefit of understanding kind of small model systems for different types of behaviors you can see in transformers, or like more generally like sequence processing models on a small scale. And the motivation for this is maybe we've seen this plot a couple of times before, that kind of there's this nice predictability for these models that solve many different tasks, that if you add more compute, you sort of get out more performance. But at the same time, kind of this predictability is contrasted with these specific tasks where, okay, like down the line, if you add more performance, you might be able to solve the specific task, but it's kind of unpredictable or harder to predict whether like you just need a little bit more of performance or not. And kind of a nice example I like to give for this is that sometimes your model might be able to solve a task like this. So you can kind of think of this as computing in like calendar space. So 3 months after November is February, supposedly. And on this prompt, you would get, like on one of these big models, quite a high accuracy. But then at the same time, if you just formulate the question differently, this fails. Like it doesn't do better than random, essentially. And kind of motivated by this, kind of asking why there are these kind of failure modes and capabilities and how they arise is kind of a question to look at. And if we look at a specific task, we might actually want to understand what is happening internally, kind of beyond the scale that is applied over all tasks, but kind of for the specific task. And then we can ask, okay, which features or mechanisms did the model learn? And over the past years, there have been many developments in kind of this idea of interpreting the internals that are very empirically based. So you can kind of look at, okay, how important are specific aspects of the input? If you have a specific neuron, which are kind of the sentences that are activating highly. There's kind of this understanding that the representations in language models open some sort of, like geometry that's representing some semantics. And then there's kind of this second set of ideas that are like, okay, actually, we have all these interacting components in the larger models, and trying to understand, for example, how things are copied from one place or another, can actually attribute responsibility to some specific parts of the network, and you can kind of do this on a very low level. You can find a mechanism for induction heads. You can kind of go up a bit and try to identify a circuit that is sort of predictive of like a specific task, like identifying like the object in a sentence. Or you can even go beyond this, and in cases where you have a hard time understanding actually that only a few components are responsible, kind of in a very logical way, you might say, okay, like there's several heuristic features that the network is kind of putting together that help kind of come together for the final solution. And kind of the question that I'm interested in is, when you have these different types of internal mechanisms, how do they depend on external factors in the sense of changing the model scale or changing the architecture or changing the training size? And of course, I'm not going to give like a comprehensive answer to this. So this talk is going to kind of take 3 different perspectives on and 3 different problems that kind of fall under this category of actually understanding the internal mechanisms. And I'm kind of going to go through them to kind of equip you a bit with the intuitions that I find from these tasks and model settings. And I'm starting with the first one because I think this one's sort of the closest to what we've seen so far. So what we're doing here is we're using kind of this high dimensional limits and a single index model to actually understand kind of how the input properties are being used by the network and how kind of the algorithm or the mechanism you're using changes as you change the sample complexity. And the different types of information of the input that I'm looking at are the semantics of the sentence, because kind of whether you change the meaning of the word changes the outcome, of course, and the positions in the sentence. So whether you kind of jumble stuff around, it like also makes a difference. And then the question is a bit like, how do you process these types of information in the model? And small model I'm looking at here is an attention layer. And to be a bit more precise, I'm going to take this input sentence where every token is represented by this vector in d dimensions, and kind of the sentence length is L. And then I'm going to apply some sort of attention matrix that actually mixes those tokens together. So you have like an L by L matrix that you shuffle to get your context vector kind of the same dimension as your input, and then sort of depending on the weight, y1 will be a combination of the x1s. And this is like one of the, or like the family of architectural styles that is being used in these transformers. And the input, the way in which you create this matrix depends both on the location of the token, so kind of the value of one of the entries of this score matrix, and the tokens themselves, so kind of what they mean. So ij, the positions, and x, the tokens. And then you could think that when you learn a model, it might learn to implement something that is mainly putting an emphasis on the semantics or on the positions, or it might just kind of do one of them. And the question we're asking is if in this model, the attention learns to implement like a more positional or a more semantic mechanism depending on the sample complexity. And to do so, the data model that we're employing is basically kind of the one that I showed you before, in the sense that we really just have kind of this input x, which is the Gaussian tokens that are a priori not correlated. And then we apply this target attention, so this matrix S, which contains both of a positional term, weighted by this omega, where A is kind of a term that is only dependent on the ij, and then this other term here, which is kind of mimicking, in some sense, the dot product attention, because it only depends on the semantics. It doesn't really depend on where you are. So we can kind of interpolate between a target that requires only one of these properties. And then when we go on to learn this model, we kind of specify a mismatch between the student and the teacher, where here, instead of kind of having this fixed A matrix, we have these vectors P that come into the creation of this matrix A, the matrix S, like the attention matrix, and they are some sort of positional encodings that allow you to actually use positionality of the model to fit your teacher. And then we care about empirical risk and kind of the local minima that this risk has, in order to understand which kind of algorithms can be implemented, or like in some sense they're like representatives of the mechanisms. And then kind of the interesting part is how does how do the minima change depending on the sample complexity and these higher kind of macroscopic properties in the asymptotic limit. And here we kind of take the dimension of the vectors and the sample size to infinity together. And I'm not going to go into the details, but kind of the two observables that come out of these fixed point equations for the local minima of this empirical risks can be characterized by two observables, where the first one characterizes, actually, water, characterizes whether you are, okay, now I can see, whether you are the kind of overlapping with mu, which was our vector that encodes the positionality, or whether you're kind of close, your learned vector is close to the q, which was kind of the vector you need to learn it for the semantic mechanism. And then what we find in the landscape for these observables is that we can characterize minima where one of them is mostly independent of kind of the semantics, and one of them is mostly independent of the positions. And this allows us to actually understand that as we kind of change the sample complexity and as we compare the value of the loss between these two, that there is this transition where kind of, so if you remember, omega was like how positional the target is or how semantic. And as we increase the number of samples we have available, the difference in the train error between these two minima changes from positive to negative, which means that at some point the positional minimum is kind of the lower one, and the other one is the semantic is the lower one. And you can kind of cross-cut here for a fixed omega, you can see that this means that the test error undergoes a sudden loss as you kind of increase the sample complexity. And you basically, this one is learning the positional mechanism, and then when the other loss in training error becomes smaller, it also has like this associated smaller test error. So this is kind of a nice example where this type of analysis can tell you, so it's this nice example where the model actually has to choose between two different mechanisms and can't implement them at the same time. Wow. Anybody has something to speak? So, no? Yeah?
Like sugar?
Yeah, like, I think. That's perfect. I should have provided myself. Sorry. But please go ahead and ask your question. sorry, I should have said this. So the length here in our analysis is constant. So this this plot is like only for, I think, L equal 2. And there, yeah, you just have 2 input sequences. Like, no, 2 tokens per input sequence. And the number of samples and the dimension is what kind of goes to infinity together. Okay. Thanks a lot. So yeah, kind of in this first example, you can actually kind of see how this learned algorithm is influenced by that sample complexity. And kind of based on this work, which is a static analysis, right? So there's nothing said about the dynamics. We just kind of understand where the minima are in the loss. Some of my colleagues have kind of Aaron, do you think you want to do a quick switch? Yeah. Yeah, I think that's better. Instead of like coughing in front of you. This is like also a good point. So there's 2 things left. So you take this.
I saw one error, so that's what I was doing at the back there.